Hello students, let us begin lesson 3, the derivative. First, let's begin with a familiar concept of average rate of change, which is defined like this and visualized like this. I hope everybody remembers. No? Well, okay, that's okay. We can start as if this were new. The average rate of change is defined as the change of output over the change of input. Equivalently speaking, is delta y over delta x, the difference of y coordinate over the difference of x coordinate, rise over run. Now here, this Greek letter delta means the difference or the change. It's not a multiplication by delta times y over delta times x so that we can simplify as y over x kind of like this. No, this is wrong. You can't do this. You cannot cross out delta, because this is not the multiplication. These deltas actually mean the change, the difference. So what is delta y? That's the difference of y coordinate. So it's y2 minus y1. That's delta y. Likewise, delta x is x2 minus x1. So what do we have? The difference of y coordinate over the difference of x coordinate, rise over run. Remember, this is a slope formula, and not coincidentally, we get the slope as you see down here. Now let's look at this graph a little bit more closely. This originated from the graph of y cos f of x, blue, and these 2 points are a comma f of a and b comma f of b respectively, instead of x1 y1 versus x2 y2. So the difference of y coordinate is f of b minus f of a, that's the numerator, and the change of x coordinate is b minus a, and that's the denominator. So this quantity here, f of b minus f of a over b minus a, is the average rate of change, delta y over delta x, equivalently speaking, or slope of the secant line, again, equivalent expression. Now that's the average rate of change. What we are going to do now is to take the second reference point here, close and close and closer to first point, so that this secant line becomes a tangent line. Want to see it in action? Here we go. Something like this. Taking the second point, close and close and closer, so that the secant lines are converging into the tangent line. Do you see it? Here's an animation. So the limit is the instantaneous rate of change, and that is the slope of the tangent line. So this visualizes the slope of secant lines converging into the slope of tangent line. And that quantity is called the derivative. However, I have to do some algebraic manipulation here in order to have full scope of everything here. You see, this expression was sufficient for the average rate of change versus the slope of secant line, but historically, this is not the way people used to define the derivative. This is what people used to do. So f of b minus f of a over b minus a, all right? Into this expression, we're going to name h as b minus a, the denominator, and thus b is a plus h. So we're going to name this denominator as h. So that's b minus a. And then from here, if I flip a to the other side, then b is a plus h. And do you see a plus h? Not directly, but do you see b? Well, right there. In short, b minus a, that becomes h, and b becomes a plus h. So this expression here became that expression. Consequently, this and that are the same. This quantity here is called the average rate of change, and this quantity here is often called the difference quotient or Newton quotient. As you can see from this visualization, they actually mean the same thing. As you can see, you have two identical pictures, two identical slopes, but labeled differently. Here, a comma f of a, b comma f of b. Here, a comma f of a, and a plus h comma f of a plus h. The latter expression may look a little bit more intimidating, but that's actually the same, very same as the average rate of change, and consequently, this too is the slope of secant line. Now this is called Newton quotient because it is Isaac Newton who studied this, and that was late 17th century, I think. I don't remember the precise year. That's when he developed all the ideas of calculus. And there's a conclusion. The average rate of change, delta y over delta x, f of b minus f of a over b minus a, or this difference quotient, f of a plus h minus f of a over h, and finally the slope of secant line, they all mean the same thing. And especially from this expression, upon taking the limit h going to 0, we get the instantaneous rate of change, which is actually the slope of tangent line. See, this convergence. Here's a grand conclusion. This limit here defines the derivative. So the instantaneous rate of change of y equals f of x at x equals to a is called the derivative of the function f at a. And we're going to represent it as f prime of a. And this limit expression is the usual definition of the derivative for historical reason. But it is okay to use this usual. Did I say usual again? Maybe not that usual. You can use this alternative expression of the average rate of change, f of b minus f of a over b minus a, and define it like this too. That too is a derivative. It's the same thing. But historically, people usually define the derivative like this, using Newton quotient. By the way, here's another expression of the derivative, delta y over delta x, and both delta y and delta x are going to 0, so that we have 0 over 0 type limit. So rename those using infinitesimals, dy over dx, and define the derivative like that. And that too is valid expression. This is German expression. Leibniz is the one who created this. And this one here, f prime of a, that expression is French expression, Lagrange and Laplace. Lagrange, as a matter of fact, is Italian, but he studied everything and did all the work in France. So his influence is in France. And then this final expression here, that's English. You see, we're talking about some multicultural, various expressions of the same thing. And people had been using this for centuries, so it's too late to change any of those. You just have to learn all those and get familiar with all those anyway. All right, so much for the rate of change, and we're going to talk about the derivative in a little bit more detail in a separate video. So much for section 1.